before I get going? Okay, we have one more topic in the second law of thermodynamics. And then, so after today, I'm going to do a really long, detailed outline. And I'm going to just keep doing these long, full outlines after each section. I really encourage you to do the same thing on your own, you know. Go back to your notes, read through your notes, write outlines of what we've done. Like, really what you need to do in this class is just make connections between the different topics, you know. You have to, like, and I really think it's important that you start to see, like, words and settings and stuff, and that starts to trigger, like, I'll bet this is going this way, this is going this way, you know, that kind of thing. So, okay, anyways, this is the last thing before we do a really long outline. What the? I've never seen that before. Okay. So the last topic in the second law of thermodynamics. That's the second law for control volumes. And this one is a lot less complicated of an equation compared to the first law for control volumes. But remember, the way the control volume approach works is you deal with the stuff that's in the control volume, and then you add or subtract the stuff entering or leaving. So for a control volume, we have that the derivative of the extensive entropy in the control volume with respect to time is equal to the sum of all the Q dots over temperatures. So that's the rate of heat coming in. And this is along the whole boundary. Plus the mass flow rate at the inlet times the specific entropy at the inlet. So that's the entropy coming in, minus the entropy going out, which is the mass flow rate at the exit, times the specific entropy at the exit, plus the rate of entropy production. And this has to be positive. That has to be, yes, that has to be positive. Okay, and just like with the first law, we're going to see a lot of steady state stuff. So what does steady state mean? What? It means that, yeah, the change, that's right, the change in entropy is zero. So first, ds dt is zero. And then the second one that we had before is that mi and me dot are the same thing, and we'll just call it m dot. And then there's one more that's going to be useful. If it's in steady state, then Q dot no, not Q dot. sigma dot over m dot can be thought of as just sigma over m. So these two things are interchangeable. Okay. If you think about it, like if those rates aren't changing, then this is just a fixed amount over time. It's proportional to the fixed amount of mass flowing through over time. So it makes sense that you can just exchange one with the other one. Okay. And actually, I was about to do a Q1, and I do want to do that. So Q dot over m dot is also interchangeable with Q over m. So if you see, you can still use this equation even if you're given stuff in terms of sigma over m or heat over m. Okay. All right, so let's do two examples. So first, we have a steady state turbine. And steam enters the turbine. The pressure at the inlet is 30 bar. The temperature at the inlet is 400 degrees Celsius. And the speed at the inlet is 160 meters per second. And then at the exit, we have a saturated vapor. We're given a pressure of standard atmospheric pressure 1.01 times 10 to the 5th pascals. A temperature of 100 degrees Celsius. And a speed of 100 meters per second. Well, that's redundant to say that if it's a saturated vapor and we know the pressure, then we can just look up the temperature. But notice that in both of these two cases, we have whatever we need to look it up in a table. This is a saturated vapor at standard atmospheric pressure, a reasonably, a temperature that's really far from absolute zero. And so we could use ideal gas law. Like, we have a lot of options available. Okay. And let's say that we're given that the heat transfer per mass over some interval of time is negative 22.6 times 10 to the third joules per kilogram. The outer surface temperature of the device is 350 Kelvin. And we want to calculate the rate of entropy production over the mass flow rate. Okay, well, this is steady state, so we can use all of these facts. So I'm going to write out the full equation. ds dt for the control volume is equal to the sum of all the rate of heat flow over the temperature around the whole boundary. steady state, so I'm just going to call this m dot times the specific entropy at the inlet minus m dot times the specific entropy at the exit plus sigma dot. All right. So, well, we are given that it's steady state, so this is 0. So we have 0 is equal to, now what's the heat transfer at the boundary? If we divide everything by m dot, we have q dot over m dot divided by the temperature at the boundary, which is 350. Plus specific entropy at the inlet minus at the exit plus sigma dot over m dot. We are given that q over m is this thing, and so that's also equal to q dot over m dot. So 0 is equal to negative 22.6 times 10 to the third divided by 350 plus SI minus SE plus sigma dot over m dot. And so negative 22.6 times 10 to the third divided by 350. We have 0 is equal to negative 64.57 plus SI minus SE plus sigma dot over m dot. Yes?
That 64 is fairly legible. I think you for that sigma dot should probably fix that.
Okay, so now what do? We're trying to come up with sigma dot over m dot. Yeah, just go to the table. Could we do anything else? Since, well, it starts out as steam, it ends as a saturated vapor. So we could use the ideal gas law for this if we didn't happen to have a table for this. Remember, we have an expression that relates changes in entropy to changes in temperature. But let's just go to the table, which I don't have. Well, okay, so there's the table. But also for an ideal gas, we have that the change in specific entropy, if you don't have too big of a temperature range, and what's the temperature? Well, that's a pretty big temperature range. So you could do this is equal to S0 at 400 degrees Celsius minus S0 at 100 degrees Celsius plus natural log C times the natural, am I doing this right? C times the natural log of T2 over T1. Is that equation right? Give me 1 second.
On one of the homework problems, I had a different, like 500 degrees, and I still used ideal, and
And
it's
you-
still a very close answer,
Yeah.
to be honest.
Yeah, I don't have that equation written down. Okay, well, let's go to the table. So we have 30 bar and 400 degrees Celsius. This is water. We're starting out with vapor, steam. So 30 bar, 400 degrees Celsius. And we have a specific entropy of 6.9212. So our S1, that's our S inlet, equals 6.9212 times 10 to the third because it's in kilojoules. So this is joules per kilogram Kelvin. And our S exit is a saturated vapor at 100 degrees Celsius. So at 100 degrees Celsius, the specific entropy for a vapor is 7.3549. Times 10 to the third joules per kilogram Kelvin. And so we got 0 is equal to negative 64.57 plus 6.9212 times 10 to the third minus 7.3549 times 10 to the third plus sigma dot over m dot. And so sigma dot over m dot is 498. And that is in joules per kilogram Kelvin. And this has to be positive, remember. It would be 0 if you had a internally reversible process. Any questions about that?
There are no internally reversible that we know,
Right. Right. But you can get close, you know?
Yeah.
Right. And this value tells you something about the efficiency of your cycle or your system, you know? You're trying to find ways to get this close to 0. This represents the amount of inefficiency you have in your system. All right. One more example. Okay, so let's say we know we have this device, and we have input values and exit values. The question is this a nozzle or is it a diffuser? Remember that the equations for nozzles and diffusers are basically the same. They exchange enthalpy for speed of the fluid. The question is just, is it faster and higher pressure at the beginning, faster and lower pressure at the beginning, or slower and higher pressure at the beginning? You know what I mean? So what we're going to do is we're going to use the first law for control volumes to figure out the properties that we're missing. And then we're going to use the second law for control volumes to figure out which direction is possible based on the entropy production. Okay, are you with me on that? All right, so at state 1, I mean, we don't know that this is the first state, or we're trying to figure out which one happens first. But let's say that we have steam at 60 bar and a temperature of 400 degrees Celsius and a speed of 30 meters per second. And it goes through this process and we end up with a saturated vapor at 30 bar. And we want to know first, what's the speed at state 2? And second, which of these happens first? Which way does it go in time? All right, so for part A, how do you know that you're not going to use the second law for control volumes for part A? Remember, the second law for control volumes is a pretty simple looking thing. It doesn't have a lot of variables in it. If you're not trying to calculate produced entropy or something about entropy, it doesn't really help you. Okay, so the only thing that has speed in it at all is the first law. So we're going to start with, I didn't give you the conditions. So this is steady state. That's going to be important. No heat transfer. And since it's a nozzle or a diffuser, it's rigid, so no work is going to be done by this control volume. And there's no change in potential energy. No significant height change or anything. Okay, so dE dt is equal to Q dot minus W dot plus Mi dot times the quantity Hi plus Vi squared over 2 plus Gzi minus Me dot times the quantity He plus Ve squared over 2 plus Gze. Steady state means that goes away. These mass flow rates are the same. There's no work done by the control volume, no heat transfer, and no significant change in potential energy. And so we have Hi plus Vi squared over 2 is equal to He plus Ve squared over 2. Okay, well, I have it written as an inlet and an exit. We're going to plug values in, we're going to have to choose one or the other, and just see if that holds. So let's assume, or maybe a better word is suppose, just for the calculations, that state 1 is the inlet. And state 2 is the exit. Okay. We have everything we need to look up values. So we can look up the specific enthalpy at state 1. And so, let's see, inlet. Yeah. So we have 3177.2 times 10 to the third plus the speed at state 1 squared over 2. So that's 30 squared over 2 is equal to, do we have what we need to look up the enthalpy at the exit? Yeah, it's a saturated vapor. We have the pressure. And so we can look this up, and it's 2804.2 times 10 to the third plus the exit speed squared over 2. So Ve squared is 2 times the quantity 3177.2 times 10 to the third minus 2804.2 times 10 to the third plus 30 squared, that's 900. I multiplied both sides by 2, so I got rid of the dividing by 2 there. And so you get that the speed at the exit is 864.2 meters per second. Don't put your hand in front of that.
I'm assuming you already squared it, so it's not V squared.
Yes, I already took the square root. Thank you. Okay, well, we suppose that this was the exit and the other one is the inlet. So now we're going to check. Okay. So the way we have it, what did we suppose that this is? That this is a nozzle or diffuser?
Got faster.
It got faster, right? So it's a nozzle. Yeah, that's right. So we're going to check it. So we supposed nozzle. Let's try that first. Okay, so the second law for the control volume says ds dt for the control volume is equal to the sum of all the rates of heat flow divided by the temperature around the boundary plus m dot times the specific entropy at the inlet minus m dot times specific entropy at the exit plus the rate of entropy production. Steady state also means this is equal to 0.
Q0.
Yep, Q is equal to 0, so this goes away. And so we have that the specific entropy at the exit minus the specific entropy at the inlet is equal to the rate of entropy production over mass flow rate. Again, we can just go to the table with this. So our SE is 6.838 times 10 to the third. Our SI is 6.187 times 10 to the third, which is greater than 0. So we kind of supposed right, you know. This is a nozzle. If we imagine that it was going the opposite direction, we would get the exact opposite result, you know. And the negative value for entropy production means that it's not possible. Anybody have any questions about that? Okay, so that's the end of the second law. Next time, I'll start a long, detailed outline of where we are so far, and then we'll start getting into some specific power cycles and stuff like that. Okay, let's do the quiz.